Hello Gators, this is 1.8 determining limits using the squeeze theorem and connecting multiple representations of limits. Let's take a look at what we call the squeeze theorem. Sometimes it's called the sandwich theorem. When we're working with three functions, and two of the functions have the same limit. So we have this function h, this function f, and they both have the same limit at c, getting close to c. If there is another function that's between them, sandwiched between them, and it will behave the same way at C as the one below it and above it does. Let's take a look at an example. We have two graphs, an f of x and a g of x, and I have graphed them, one in red and one in blue. And we have a third function, k. We don't know what it looks like. We don't have the algebraic representation, but we know that k is between these two functions when we're close to 0. So can we find this unknown limit for this function that we know is trapped between? And the answer is yes. As long as it meets the criteria of the theorem, and it does, we can say, since we knew the one above it and below it, we know its limit, and its limit is above and below here. This limit is equal to 0, and this limit is equal to 0, so this one must be 0 as well. They're all wanting to cross at the origin. All right, let's take a look at this limit. It looks pretty complicated. If we were to substitute, this would be 0, and then this would be cosine of an undefined situation, so we can't do that. So let's use the squeeze theorem. First, let's just examine this part of the limit right here. And cosine of 1 over x squared is pretty scary, but we know something about cosine. And remember, the graph of cosine looks something like this. It's this oscillating function right here. And we know that its lowest value is -1, its highest value is 1. Okay, so I know something about this. Now I'm going to multiply all three sides by x squared. So this will be -x squared less than or equal to cosine of 1 over x squared. And I want to multiply this by x squared as well. And less than or equal to x squared. So I've multiplied this side by x squared, this and this. Now I'm going to take the limit as x approaches 0 of all of these sides of the inequality. And I know that this limit will be 0 and this limit will be 0. So this one that I don't know is trapped between them, and I know that this limit will be equal to 0. Okay, let's go ahead and take a look at this next example. We have two functions, and we're being told that g of x is less than or equal to f of x, which is less than or equal to h of x. So this is less than this, as long as we're close to the number 2. So let's go ahead and find the limit of g of x at 2. At 2, this will be -4 plus 4 minus 3. So this limit will be -3. And then this limit will be 2 times 2, which is 4, plus 1, and this is 5. So we have this situation. And we can see that we're not getting squeezed here. So can we find the limit of f of x? And the answer is no. What is limits does not exist, not with the information that we have. We just don't know what it's squeezed in between. Now let's take a look at some special trig limits. Let's take a look at this, and the way I'm going to help you is I am going to actually use a calculator to help us figure out this value. So let's go ahead and we are going to find this one, and then we'll find this one. So using a calculator. So I have y equals sine of x over x. Make sure my mode is in radian mode. And there I have y equal to 1. And I'm going to go to the graph. And this is what the graph looks like. I'm going to press trace. And let's just look at the y values. So as we get closer, it looks like it disappears and then goes there. Well, let's look at the table. And the table will reveal a little bit more. It looks like we get an error here, which that makes sense because when we get closer to 0, the denominator becomes 0. But the value before and the value after looks like it's getting closer to the number 1, which is what we're saying right here. Okay, let's look at the other limit, which is this one. Let me turn this one off. And then go ahead and turn this one on. And let's look at the graph. And here's our graph. Let me go ahead and press trace. Again, I'm going to do it a little before. And it looks like it disappears at 0, which again, we understand why it's disappearing. Let's look at the table. And we can see the table. We have values getting close to 0, values afterwards where we're getting close to 0, but at 0 we don't have it. So we do have a limit. We just don't have a value at that thing. So our calculator is telling us something about these values, but I would like to take a moment to prove it to you. But before I prove it to you, I have to take you back to a little bit of algebra and geometry. So I'd like to find the equation of this line right here, and it's y equal to mx plus b. I know the slope is change in y over change in x, and that'll be sine over cosine x, and our b, our y-intercept is 0. I can just say tangent of theta here, x. At that point where x is equal to 1, because this is the unit circle, as x equal to 1, if I put 1 in here, I'm going to get y is equal to the tangent of theta. So this point here is 1 tangent of theta. I want to remind you of something in geometry. Area of a sector is m over 360 times pi r squared. That's what we call a portion of the circle. Since we're working in radians, we're going to change the 360 to 2 pi, and we're going to call m theta. And we can do a little reducing, and we get theta over 2. So the area of a sector when we're working with radians is theta over 2. Okay, that's going to help me with this. Okay, we have 3 areas we'd like to talk about. I'd like to talk about this area of this big triangle. Area of the triangle is 1/2 base. The base is 1, and the height is theta. So this will be theta, tangent of theta over 2. The area of the sector right here, that piece of the area, is theta over 2. I just proved that for you. And the area of the triangle is 1/2 base. Base is 1. And the height right here is sine of theta. So this is sine of theta over 2. So let's go ahead and rewrite. Let's divide everything through by sine of theta. So I'm going to, let's go ahead here. I'm going to divide by sine of theta here. I'll put sine of theta in the denominator here and put sine of theta down here. And I'm also multiplying by 2 over it so that I can get rid of the 2. 2 over. 2 over. Okay, so now this becomes 1 over cosine theta and theta over sine of theta, and then this becomes the number 1. Okay, now these are all greater than symbols. Now I'm going to do the reciprocal, and when I do the reciprocal, I have to change my inequality. So then this becomes this. So now I have this, I have these 2 functions, that this function's caught between these 2 functions. I'm going to take the limit as theta approaches 0 of this side and in the inside. And I can see that the limit as theta approaches 0 of cosine is 1. The limit of as theta approaches 0 of 1 is 1. So this limit that I showed you on the calculator, but now I'm proving with a proof, is equal to 1. All right, so I didn't prove this one. This one is 0. And this one is 1, and the reciprocal will be 1. And then this one is going to be 0 as well. And the reason why is this is the same thing as the limit as x approaches 0 of the opposite of 1 minus cosine of x all over x. If I factor out a negative 1, this will still go to 0, and so the answer is still 0. Okay, we're going to use these trig limits to figure out this answer. Now, what we need to understand is the sine of an angle over the angle is going to be equal to 1. So here's the angle 3x, and I really need another 3x. So what I'm going to do is I'm going to do some algebra manipulation. And what I'm going to do is I'm going to multiply by the number 1. So I'm going to multiply by 3 over 3. 3 over 3 won't change anything. Okay, now this part right here looks like this, this rule for sine of x over x. So this is going to go to 1, and then 3 times 1 is 3. All right, let's look at this next one. We're going to do the limit as x approaches 0, and we're going to do sine of 7x over 1 times 1 over sine of 9x. Okay, and so what I'm going to do is I'm going to multiply by the number 1. I'm going to write 7x times 7x. I'm going to write 9x over here. I'm going to write 9x over here. So I'm multiplying by the number 1. This is going to go to 1. This is going to go to 1. The x's are going to reduce, and I'll have 7 over 9. Okay, and on our last one, I'm going to take the limit as x approaches 0. And this first one I'm going to factor. And this is a difference of 2 squares. And I can use factoring, and then I can use reducing. So here's my canceling. And I forgot I have an x right here, right there. And so this is just this thing right up here, and that is equal to 0. So here's some examples on how to do these problems. All right, I'd like you to take a moment to stop the screencast and see if you can figure out all of these values. And here are the answers. I took a look at the limit on the left, on the right. They were the same, so the limit exists. I took it at the left. In the left, it looks like it was getting close to the number 6, right here. And over here, as close as I could get, it looks like I was getting close to the number 6. So I know at the value 5 it's 1, but we still say the limit exists because we're getting closer and closer on the left and the right. Over here, the left and the right were not the same, so I say the limit does not exist. Let's take a look at finding this value. Sometimes we have to do substitution to help us. So this is 4, and we're going to go from the left side right here. So I'm going to choose a number like 3.9. So I'm going to write, I'm going to figure out what 3.9 minus 4 over 3.9 minus 4. And I can see that this is going to be negative 0.1, and this is going to be absolute value, and then negative 0.1. So the answer will be negative 1, because this will be a positive, this will be a negative, so you're negative. Let's try again at a 3.99. So this will be 3.99 minus 4 all over 3.99 minus 4. So that will be a positive, negative, or positive 0.01. This will be a negative 0.01. So the answer is still negative 1. So this answer is negative 1. Sometimes it's just good to use substitution, especially when I don't give you the ability to use your calculator. Okay, last thing, greatest integer function, or what we call the floor function. It's a really complicated step function. So let's take a look at what happens at 1/2. And when we look at what happens at 1/2, as we get closer from the left side and the right side, the answer is 0. Okay, here 1 is a little bit more complicated. As we go from one side and the other side, we can see it's 2 different limit values. So this is a does not exist. For the integer function at all the integer values, we do not have a value.